All right, it's time. She's here. Welcome back. Sorry, I still haven't gotten to the test yet, but I'm gonna hopefully do them tomorrow. And yeah, we have homework due tonight. And sorry again, I forgot to post it in the Gradescope, but I'm gonna do that right away after class. It's all just number one really in the book. I don't know why they tried to do me like that in this section only, but I thought it was cute. We were talking last time about NFAs and regular expressions and kind of going back and forth between them. Going from a regular expression to an NFA is fairly straightforward if you know how to handle the operations, and you just have to remember the plus makes like two branching paths. The star makes, the burger shape, and so on. The other way round is a bit more tricky, and that is to convert an NFA to a regular expression. We did some examples last time. Maybe I'll just sort of as a warm-up. Let's try. Here's a NFA. I want to make a regular expression out of it. So this is similar to one we did last time. All right. So you want to look at this and decide for yourself, what are all the ways that you can make it from the starting state to the accepting state? And the answer in this case is, well, first of all, you must begin with A. And then once you get here, I suppose you could just stop and not do anything else, but there's also kind of two different loops you could do. You could go around this B a bunch of times and still be accepted, or you could go around this loop of three A's a bunch of times and still be accepted. And you could do any combination, you could do some B's and then some of the three A's and then some B's again. Anyway, how I would write all of that is, first off, A first. You must begin with A. And then there's some amount of stuff which I'm going to put inside of a star that represents those two different types of loops you could do. And what are they individually? One is just B, and then the other is AAA. So I'll put a B plus AAA, or you could say A cubed if you prefer. I think it's something like that, right? You must do A first, but then after that, you could do nothing, or you could do any iteration of B by itself or three A's at a time. All right? I hope everybody remembers this. How about let's make it a little fancier? How about I'm just going to add some more stuff onto this, if you don't mind. Let's try something like this. How about that, huh? So this one now has two accepting states, which makes it a little more complicated. And there's also this loop over here, all right? But we are still going to try and think of the main question you should be asking yourself, just like before. What are all the ways I can make it from the starting state to the accepting state? Now, in this case, there are two different accepting states. So I'm just going to consider each one separately and put a plus in between them. Because what are all the ways to be accepted? Well, you could be accepted here, or you could be accepted down here at the other one. And so my answer is going to look like sort of a bunch of stuff plus another bunch of stuff. And those two things are mostly unrelated. Some of them represent how you could be accepted in this one, and some of them represent how you could be accepted in the other one. So maybe let's say as the first part here, I'm gonna that'll be this one down here. So what are all the ways you could get to this one down here? Well, you got to do A followed by some more A's, and actually before you do any of that, you could do this, A and then B. So there's a little loop here. So I would write this as something like first, and this is optional, but you can do AB star, right? That represents this little loop right here. And then after that, you must do A, followed perhaps by more A's if you want. So I would say AB star, A star, right? That part kind of represents this accepting state. Those are all the ways that you could get to that accepting state. And then the other one. What about the other one? Well, the other one is really just like the one that we just did. I mean, it was a variation of that. Except the difference, one difference is in the other one, you could also begin with this stuff before you do the first A. So I'm going to, again, begin with AB star and then say A, this stuff, right? So it's AB star, AB, the whole thing star, of course, and then A, B plus, I'll write it as A cubed this time. All right, that's the other, so this part over here refers to that accepting state. All right, any thoughts about that? These can be a little tricky, especially if the diagram is super complicated. But it is always possible to do this. It might end up being really complicated, but it all has to do with just kind of keeping track of where are the loops that I'm allowed to do along the way as I get to the accepting state. All right, I got a couple for you to try, and then I think we'll be ready to move on to something a little different. How about, so your job in both cases is make an equivalent regular expression from these NFAs. There's one, and here's another one. There you go. See what you think. I'll give you a hint. The first one starts with B. first A star for the little loop? Yeah, so I would write that as the little loop and then plus with the other loop, because you can do either one, and you can. Yes, that's great. And I think I should. It's not long. Because of that stuff, it's not necessary. Yeah, if you have that one, then it's also. No, I don't think that's wrong. I would say this is not necessary. This stuff, that one you do. Yeah. All right, let's talk about them. I see some good answers. So for the first one, there are different ways that you could write this that are still correct. So it may be if you are not getting exactly what I say, it doesn't necessarily mean that you're wrong. But the way I would say this one is, you start with B, and then after doing B, there are some loops here. You can either do this, the little loop, or this larger loop. And so I'm going to make a plus A plus, this A represents the little loop, and then I'm going to put a star on the outside of parentheses here. It's like that, right? So this represents this little loop, and then this loop over here, A followed by B, but you could do extra A's in the middle. I would write that as A star B. So this is how I would have written that one. Like I said, you may have written something a little bit different that's still equivalent to this, but to me that's the most reasonable way to express that. Any questions about that one? Anybody feel like your answer is better? It might be. All right, and this one over here, I would say you begin by doing either this loop or this loop. Now this loop is just A or B, and this one is AB. So there are really, I would say, 3 loops, A or B or AB, and all of that goes in a star because you can do any combination of those one after another. And then followed by A and B. So like that is how I would write this. Right. This one actually, now that I write it like this, I notice that this could be simplified. Like this part right here is really the same. I wouldn't really suggest doing this, but this is really, as a regular expression, it's the same as that. Because A plus B star already allows you to create any string out of A's and B's in any combination. This one, what's the difference between these two? Well, this one says, yeah, you could use A's or B's, or you could use A followed by B. All right, but that's like already allowed from this one. So this is kind of redundant, although it makes sense to write that given that this is what the diagram said. But the fact is, this part of the diagram is redundant with this, right? If you want to do A and then B and then end up here, you could also just do A and then B up here. So this is sort of redundant because the diagram is kind of stupid to begin with. All right, any thoughts about that? As usual, just like NFAs and DFAs, it is possible to write a regular expression that's kind of like more complicated than it needs to be. You know, it's possible to sort of simplify them sometimes. All right. Anyway, this is something you'll see a few more ones like this on your homeworks, but I hope that everybody is convinced at this point. This is always possible to do. Sometimes it can be difficult to analyze all the possible sort of ways that you can make it from here to there, and considering all the loops is really a pain sometimes. But this is always possible to do. By this, I mean convert NFA to DFA. No, I mean that is also possible. Convert regular expression. No, NFA to regular expression, sorry. Convert NFA to regular expression, right? It is always possible to do. I don't really want to talk in super specific terms about this because there's a lot of technicalities. You can read about this in the book, and actually the book also recognizes that it's kind of stupidly technical, and this part in the book is in the appendix because even the author of the book knows that you don't want to read that stuff. I hope that everybody's convinced that this is, in principle, always possible to do. It's kind of a pain to try to imagine all possible eventualities but it is possible to do, converting a NFA to regular expression. What this means, so last time we talked about converting regular expression to NFA. That is always possible. And furthermore, it's also possible to convert any NFA to regular expression. What that means is, like both of those things together means that NFAs and regular expressions are basically the same. They're interchangeable in terms of what kinds of languages they can express. All right, so that means this has a name. This is called Kleene's theorem. And it says that the set of languages expressible by regular expressions is the set of regular languages. All right. Kleene is this guy who invented regular expressions. And why did he call them regular expressions? It's because of this. A regular expression defines a regular language. So just like NFAs and DFAs, regular expressions are yet another way that you can represent a regular language. So in more like, colloquial terminology, I would just say it like this. Regular expression is equivalent to NFA/DFA. In terms of what kinds of languages you can express using these various frameworks, they are all the same. All right. Here's a cute example. What this means is, for example, anything that we've ever done using NFAs and DFAs can also be done with regular expressions. So this means, for example, there is a regular expression on the alphabet 0, 1, which matches binary numbers divisible by 3. Why do I say that? It's because we had a DFA that accepts only binary numbers that are divisible by 3. And if such a thing is possible using a DFA, then it is possible using a regular expression. So regular expressions, we don't usually think of them in this way, but they are kind of like computing machines, like they can do this kind of divisibility computations or whatever. Can we actually find that regular expression? Find it. How would we do that? Well, I would remember what the DFA looked like and then convert that to a regular expression. So I will refresh our memory. What the DFA looked like is this. This is the accepting state, and then it was like that. I think I'm just going to make sure I get this right here. And then zeros here. This we talked about like long time ago, in the first week of class or something. This is the DFA, which accepts only binary numbers which are divisible by 3. Can we make this into a regular expression? Yes, we can, just like the ones we were doing before. It starts in the accepting state, so we don't have to worry about sort of extra stuff at the beginning, but then we just have to talk about various loops you can do, right? There is, of course, this little loop here, 0, and then there's this kind of loop you can do over here, which actually has a lot of sort of choices. You could just go 1, 1 and come back, or you could go 1, 0, 0, 1 and come back that way, or you could go 1, 0 and then some more 1s and then 0, 1. Anybody want to take a stab at writing that as a regular expression? I would say, here's how I would start. 0 plus some other weird stuff and then a star. So this 0 here represents the little loop 0. And then what goes here represents all of this other stuff. Anybody want to throw something out there? Yeah?
Could you do plus 1, 0, 1 star, 0, 1?
I like this. 1, 0, 1, star, 0, 1. This is not quite what I would say, but this is, I feel good about this. This is pretty good. That means you go here, here, do some ones, here, here. Great. Anybody feel like that's not entirely right? I feel like this is not all there. Yeah?
Because we got to be able to go 1, 1.
Yeah, we do want to be able to do something like 1, 1. Which this doesn't allow because this requires the zeros. And actually, we also want to do something like 1, 0, 0, 0, 0, 0, 0, 1, which this again doesn't allow. I would say what we need is for the zeros also to somehow be part of a star. Anybody see how you could make that happen? Actually, you can, small change to this. You want it so that the zeros, if you put the zeros also somehow inside of a star, then they become optional and they also become repeatable. Yeah?
Put parentheses around zeros.
Okay. You mean here? Like that? Yeah. I think this will do it. And then, come on. Back it up there. Put a little star there. Yeah. This, I think, is the simplest way to write this. Excellent. Yeah, so that regular expression right there will match only binary numbers divisible by 3. Kind of cute, in my opinion. Any thoughts about that one? Anything you can do with the DFA or NFA, you can also do with regular expressions. Excellent. All right, I'm ready to move on and talk about something really and truly different. I feel like, I don't know if this theorem here, or this right here, regular expression is equivalent to NFA, DFA. I don't know if you feel kind of let down by this. I feel like this is kind of a bummer in the sense that when I cast my mind back to all that we've ever done, we've been through a lot, you and me, but actually it was all just like the same stuff over and over again 3 times because everything we've talked about so far has been about regular languages. And you can do with DFAs, you can do with NFAs, you can do with regular expression, but on a certain, like, from an abstract point of view, those are really all the same thing. And so, but that's not what this whole class is about, right? So what I want to begin talking about is non-regular languages. Finally, something different. Non-regular languages. I have maybe once or twice hinted that not all languages are regular. It's not possible. Like there are some languages which you just straight up cannot do on any NFA or DFA or regular expression. And I will tell you an example. I'll just tell you, although it's not so easy to say. There are non-regular languages. One example is, this is sort of the simplest example. If someone, if you're talking to someone at the club and they're like, oh, really? There's non-regular languages? This is the one that everybody will be talking about in the VIP lounge. This is like the standard example of a non-regular language. A to the n, B to the n. This is different from A star, B star. That, of course, is regular because I just said a regular expression for it. Anything you can say a regular expression of is regular. But this is A star, B star is different from that because this requires that the exponent here is equal to the exponent here. So this only includes things like a squared, b squared, or a cubed, b cubed. It doesn't include a squared, b cubed, something like that. All right. The powers are the same is super important. If you let the powers be different, then it's the same as a star, b star, which is a regular language. All right. So what we're going to talk about, there is a very nice technique for demonstrating that a language is non-regular. If you think about it, this from a theoretical point of view is something that should seem very hard to show something is not regular. because what regular means is it can be accepted by some DFA or NFA or whatever. If you want to tell me that this right here is not regular, you have to somehow convince me that no possible NFA accepts this language, or no possible regular expression can generate this language. And if you were going to try and prove that, you'd have to somehow like consider all possible regular expressions and then explain why they can't do this. And that's not something that, like, that's super abstract to consider all possible regular expressions or all possible NFAs, all right? But we do have, there is a very nice technique, and this is something that's like very, I think it's a really cool idea, and it has a cool sounding name, or at least a strange name. This is a Polish name. I believe I spelled that right. Yes. This is, so in Polish, the RZ sounds like Z, and the B sounds like B. So this is Brzozowski. This is called the Brzozowski derivative. I am just going to call it the derivative. All right? This is not the same as the derivative from calculus, although we use the word derivative, and we're even going to write like d over dx for this thing. It's not the same as the derivative. There are reasons why it's called the derivative, which we'll get to eventually. Unfortunately, we're going to have to talk about the derivative for a little while before it even comes back to this business about showing that a language is non-regular. So I hope you will be patient as we just discuss, sort of from an abstract point of view, what the derivative is all about. And then eventually we'll come around to showing how this is actually super relevant to the question of which languages are regular and which languages are not regular. Anyway, this derivative is all about, this is sort of the answer to a question that nobody asked. But the question is, what happens if we move the starting state in a DFA or NFA? I'll just say DFA. What happens if we move the starting state in a DFA? This sounds like a random, useless question, but it turns out actually this is the basic idea behind the derivative, and it turns out to be super useful. Although it's not obviously a very interesting question at all. What happens if we move the starting state? So in order to think about this, I have an example. So I'll call this M. This is, a slightly complicated DFA. All right, it's basically this, but I want it to be a DFA, so I have to insert some more arrows. All of the other arrows go to a permanent failure state, which I'll just put down here. So there's a B going there, and then A's from all of these other ones. And a A-B loop like that. All right. So the part of the diagram which matters as far as which strings are accepted is really sort of this part, right? Everything else is a failure. Can someone say like a formula for this? What are the strings that will be accepted here? What do you think? A, B to the 3n. Yeah, I like that. A, so you must do A first and then 3 B's at a time. So you could say A, B cubed to the n, or what he said was A, B to the 3n. Great. Yeah. 1A followed by some multiple 3 B's. All right. So this is my original DFA with that as the starting state. I would like to consider, what if I move the starting state? That's what I'm talking about here. What if we move the starting state, instead of here, put it here so that it starts on the accepting state? All right? So I know this is a pain if you're writing by hand, but I'm going to copy this again. maybe I'll call this one N. Get rid of this green thing here. And this time it's the same as before, only instead of there, I put the starting state there. All right? That's the only difference. Now, what is the language of this machine? Well, this time, if I start here, it's just this B thing, right? So here, the language of this one, N, is just B to the 3N. All right? And now, actually, part of this diagram is sort of stupid now. Like, this is an unreachable state, and there's no point to even include this in the diagram, but I don't want to focus on that at this point. All right? Moving the starting state from here to here changes the language in this way. Actually, you can say it's fairly predictable how the language will change when you move the starting state. I will notice what we did here was, I like to think of this as moving this starting state through this arrow with an A on it. And the effect of that is to basically just delete the A from the beginning of the strings. That is to say, to be accepted here, you got to do this A first. But down here, it's the same, only you don't got to do this A first, right? And so I will try and somehow write this idea. So moving the starting state this is the basic idea. It's not a difficult idea. It's I would say maybe a little non-obvious, but moving the starting state through an arrow labeled, let's say A, causes all initial A's in the language to get deleted. Because you don't have to do that letter anymore, right? This is the very kind of obvious idea, but it, like I said, for non-obvious reasons, it turns out to be super useful. All right. Moving the starting state through an arrow labeled with an A causes all the initial A's in the language to get deleted. So the language that you end up with is basically the same as the original language, only all the A's that were at the beginning of the words, they are now gone, right? What if instead we moved the arrow through the B arrow? What if we move the starting state instead of to here? What if we push it through here and move the starting state down here? All right, so I'm gonna draw this picture again, yet one more time. So here, this time I am putting the starting state here, right? I will remind you, the sort of original language was A, B to the 3N, right? And we said how if you move through the A arrow, it just deletes the A at the beginning. What is the effect of moving through the B arrow? Well, for the same reason, it should delete the B at the beginning, but there isn't a B at the beginning. The effect of that is to just delete everything. So this one here, can anybody say what is the language of this DFA? Maybe I'll call this one P. Yeah? It is the empty set. Yeah, it's impossible to be accepted in this DFA because it starts on this permanent failure state. So here, the language of this one, P, is the empty set. All right? The effect of moving through that B arrow is, you could say it the same way. We remove B's from the beginning of these strings, but there are no B's at the beginning of any of these strings, and so we just get rid of them entirely. So this is kind of the somewhat strange way that the derivative works here. So here, moving through a B arrow, sorry, this is a little confusing when I write it that way. Moving through a B arrow deletes initial B's from the language. But actually, this language didn't have any initial B's, and so we end up just getting rid of everything, and we get the empty set. So moving through a B arrow deletes initial B's from the language, but no strings have initial B's. So we get the empty set, all right? Really what it is that we're doing is something like, we're doing, I would say, an operation like, it's something like, in the first case when I push it through the A arrow, so this one through A, what we get is something like x such that AX is in the original language, right? It says you find all the strings from the original language that used to start with the A, and you take the A away, and that's what you end up with, right? It's those same strings, but without the A. And when I do this through the B arrow, it ends up being all X such that BX is in the language. And in the particular example we're doing here, this is actually the empty set because there is no string BX in the original language. And so this means all X such that this happens, but this never happens, and so you get the empty set. All right? Anyway, these sets, they are called the Brzozowski derivative with respect, this is the derivative with respect to A, and this is the derivative with respect to B. And we write them in the way that everybody likes to write the derivatives. So these are the Brzz derivatives. Any of you speak Polish? Sorry, with respect to A and B. And we write it this way. So this is a general definition. So I'll write this as a real definition here. If L is a language, and let's say, A is a letter, A is in sigma, the alphabet, then the derivative with respect to A, which we write like this, of L, it equals all strings X such that AX is in L. That's the definition of the Brzozowski derivative. We can do this with respect to A, you can do it with respect to B, either way. Right. So the examples, like the particular examples that we were talking about up there were something like, what is derivative with respect to A of AB to the 3n? The answer is B to the 3n, right? And I imagine describing this as a derivative is because it's kind of like the derivative with respect to A of A is like the derivative of A is like a 1, and the A kind of goes away, and you end up with the rest of it. Whereas the derivative with respect to B of AB to the 3n, this is the empty set, because none of those strings begin with B, and this is just how the derivative handles such a situation. So when you see derivative with respect to A, it means get rid of the initial A's. When you see derivative with respect to B, it means get rid of the initial B's. If there are no initial B's, there's nothing left over when you take the derivative of that. All right? This is the derivative with respect to whatever. All right? We can also do derivatives with respect to longer strings. So I didn't write that as part of the definition. In the definition, I said that A is supposed to be a single letter, but it's no problem. We can also do something like derivative with respect to AB. That just means you look at all of your strings, and if there are any that start with AB, then you keep those strings, but you get rid of the AB at the beginning of them, right? So something like derivative with respect to AB of AB, A to the n, B to the n. This is A to the n, B to the n. It just means you look for strings which do start with AB, and you get rid of the AB, and you just tell me what's left over. Right? This is the basics of the derivative. Any questions about that? I got a bunch of examples. Let's just see. These are sort of starting off simple, and then we'll get fancy as we go, I guess. What does this have to do with what is and is not a regular language? That's for next time. We're not going to quite get that. How about some examples here? Let's try derivative with respect to a of axb. So this is the language, x is any string, right? Maybe I should write that. axb such that x is any string, so I'll say x is in ab star. So this is any string which starts with an A and ends with a B, right? And has some stuff in the middle. What is the derivative with respect to A? It means you look for all of these strings that start with A and you take the A away from them and give me what's left. The answer is just XB. That's an easy one. And really, could it get any more complicated than that? The answer is yeah, kind of. The operation is very straightforward from a certain point of view, but it's also kind of weird in the way that it works in some other situations. Anyway, here's a not weird. What about derivative with respect to B of that same thing? So what this means is look for all the strings here which start with B, take away the B at the beginning, and then give me what's left over. And the answer is nothing. There are no strings here which start with B, and so we get the empty set from this. It's because there are no strings that start with B here. All right. Okay, here's a somewhat weird example. How about derivative with respect to A of x, where x is in AB star? So this means I'm now considering just any string of A's and B's. Take the set of all possible strings. Now some of them begin with an A and some don't. The ones that don't, I'm going to ignore entirely. They will all become the empty set. The ones that do start with A, you take the A away and then tell me what's left over. Can anyone say what is left over when you do this? It's not the empty set, because there really are some things in here which start with A. You got an idea? Yeah? BX. That means if I find the strings that start with A, take that A away, what's left over, does it necessarily start with a B? I think it doesn't really, because some of them could start with, say, AA. Yeah. I would wonder, can you say anything about what's left over from those other strings? You take everything that starts with an A, you take that A away. I think what remains could be anything, right? You don't know anything about the rest of it after you took an A away. This is weird, but it's just this again. It's the same thing. This is because if you start with any string at all, and you just imagine some of them start with A, you take that A away, what's left over? The answer is, I don't know, it still could be anything, right? This is sort of strange but true. And you might think, oh, I guess then when I did this derivative, like it kept everything exactly like it was. It didn't throw anything away. That's not true, actually. This derivative throws away everything that started with a B. It's just that when you consider all the ones that started with A, there's like infinitely many of them, and you throw that A away, and you end up with another batch of infinitely many things, and it's the same batch of stuff that you started with. Very weird in my opinion, but true fact. All right? How about this? How about this? He says, how about, this one's a little easier maybe. A to the 2n, or maybe I'll say it this way. A to the n such that n is even. We got a few moments. This one's not so hard. Anyone feel like you can say what's the answer here? Yeah? Yeah, right. This is all of these strings have an even number of A's, and the operation of taking the derivative will just delete one of those A's from it, and so now it's going to have an odd number of A's. Yeah, so this would be A to the n such that n is odd. Right? Excellent. Yeah, great. That was not especially difficult. How about this one? Derivative with respect to A of, how about this? X such that, this is now A's and B's, right? X and AB star, such that X has an even number of A's. So this is similar, only there's like also B's present, all right? Anything with A's and B's, but the number of A's is even. And I'm taking the derivative with respect to A of that. What is left over? I think the obvious answer is x such that x has an odd number of a's. The question is that really what it is in this example? We start with an even number of a's. I'm not saying that this begins with an a. I'm just saying in that string somewhere it has an even number of a's. Anyone have a feeling about this? Yeah?
Is it just x has an odd number of a's? Because anything that starts with a b is thrown out, and anything with an a has one less a than it did.
Yeah, I think he said it great. Yeah, it is just, so the answer is just this same stuff, but with the word odd there. The reason is, if it starts with an A, you throw that A away, and then it's just some random string with an odd number. If it starts with a B, you just get rid of it entirely, and so you don't count that at all. Yeah, this is sort of strange but true. Sometimes these derivatives can give you somewhat weird results. I don't know if you think that this is weird or not. I think on a certain surface level, this seems kind of obvious, but if you think a little bit more about it, you'll realize, actually, this is kind of weird. But it is weird but true, all right? I got one more. How about, so here's just a simple variation. Same deal, but with the b derivative, x and ab star, such that x has an even number of a's, all right? Even number of a's, derivative with respect to b means you delete a b at the beginning if it exists. I think this, you will just get the same set again, all right? If it has a b at the beginning, you throw it away, but you still end up with an even number of a's in the string. And if it has an a at the beginning, then you throw away the entire string. This is equal to the same set again. So there are actually many sets which are equal to their own derivative, unlike in ordinary calculus. E to the x is kind of like the only game in town as far as a function which is equal to its own derivative. But in the Brzozowski derivative, there are many sets that are equal to their own derivative. All right. I think maybe we'll leave it at that. So we're going to do a bunch more examples next time of these things, and then also talk about what all of this has to do with regular languages. All right. We'll have our quiz next time also about regular expressions. See you then.